Welcome back, everyone, to our next part in dynamic programming. Hope you guys had a great break. So, if you remember from the last part, we introduced the general dynamic programming problem. Basically, if you ever have a problem that has optimal substructure and overlapping subproblems, usually it's best to take a dynamic programming approach rather than a strictly recursive one. So in the last lecture, we went over a very simple example with the Fibonacci sequence, and today's lecture is going to focus more on more interesting problems that we can solve with dynamic programming. So the first, or let's maybe start with some of the applications to get you guys excited. So one application is in finding the single source shortest path. So if you remember from a few lectures ago, at the beginning of the term, we went over Dijkstra's algorithm, and that was one algorithm to find the shortest path between two different points in a weighted graph. Well, you can actually also, and actually with Dijkstra's, that was a greedy algorithm because, we used a priority queue. We only chose the lowest weighted path as we built our our optimal path. But you can also use another approach called the Bellman-Ford algorithm, which is a dynamic programming uh, method. So that's the one application of dynamic programming. Another one is the traveling salesman problem. Maybe some of you have heard of it before. It's a very, very famous NP-hard problem where basically imagine you're given a graph with a bunch of different nodes, and the problem is to find the optimal path where such that, let's say you have a traveling salesman who wants to visit every single node on the path, but he wants to minimize the distance that he travels. So where the distance might be given as weights between different nodes. So that can also be solved with dynamic programming. Another interesting problem is in speech recognition. So there's an algorithm called the Viterbi algorithm that basically finds the hidden states that can be derived from a given signal, for example, like my voice, and those states can basically derive are what is the text that you can glean from that audio. So another very cool application of dynamic programming. And finally, or of course not finally, but in my short list of examples, there's also a problem called the knapsack problem, where imagine you are given, a knapsack and it has a certain capacity for items to hold, and you are given a bunch of different objects with a certain weight and a price. And the problem is to find what is the best choice of items to put in my knapsack such that I maximize the cost of all of those items, but I also satisfy the constraint, specifically my weight constraint for all of those items. And you can probably imagine where that would be very useful. There are, it would be very useful in a packing algorithm. Let's suppose, like Amazon or some packaging company that has a warehouse. They need to determine what is the best configuration of a lot of inventory to pack into different boxes, which we can consider as our quote unquote knapsacks. What would be the best way to optimize you know, the total cost of all of the items that are being distributed, for example. Okay, so those are just a few applications of dynamic programming, and today we are going to cover just a few relatively simple um, problems to get you guys started. Okay, so the first problem that I'm going to present you guys is the rod cutting problem. So basically imagine you're given a rod of a certain length n, and you're also given a table of prices. So each possible price, let's say 0, so if you have a length of 0, that would have that a length 0 rod would logically have no price because there's no material. And then you could have a price for length 1, a price for length 2, and so on. And well, we're gonna first of all, we're gonna assume that we can only cut the rod in integer lengths, just so that it says it's not insanely complicated with a continuous rod. And the problem really is to find what is the best way to slice this rod such that we maximize the total price of our configuration. Okay, so in my example, I have a rod of length 5, and here are my prices for different, uh, different rod lengths. And I want to find where should I cut this rod. A few different examples that I can show here is, we can cut the rod equally such that you have 5 1-length pieces, and if you're to add that up, according to the table, if you have a bunch of length 1, well, length 1 has a price of 2, so you'd have 2 plus 2 plus 2 plus 2 plus 2, and that should give you 10. Another way, and there are many, many different ways to cut the rod. Um, another one is to have a length 2, a length 2, and a length 1. If you add those up, you would get 3 plus 3 plus, sorry, that should be that should be a 2, not a 1. I'll change that, don't worry. So 3 plus 3 is 6 plus 2 is 8. And another configuration would be you have 2, 1, 1. So 3 plus 2 plus 2 plus 2, that would give you 9, and so on. So you can already kind of see that this is not the most straightforward problem because there are many, many different ways to cut up a rod, and specifically there are 2 to the n minus 1 ways really to cut a rod because at every let's suppose you have like 5. If you were to go to the at length 1, you can either choose to cut or not cut the rod. You can go to length 2, you can choose to cut or not cut the rod. And since there are really n minus 1 places that you can choose to cut the rod, and you have 2 choices for each, that's just going to result in 2 to the power of n minus 1 possible ways to cut a rod of length n. Okay, so one way that you can tackle this problem is to just enumerate all the different possible ways to cut the rod. And eventually, you will find what's the optimal way. You can just loop through all of the 2 to the n minus 1 ways to cut, add up all of the prices for each of the pieces, and just get the max of all of that. And that would be completely valid. You would get the correct answer. But, theta of 2 to the n, that's not really the best. Or it's not a very nice looking solution. It's exponential. As we keep on increasing the rod size, it's going to get pretty messy here. Very, 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 very expensive. So we're going to try to find a better approach to get the optimal solution. And the first thing to realize, whenever we're considering different methods for our algorithms, is to note that there is some optimal substructure in the rod cutting problem. Because if we know the solutions, for smaller length rods, well, you can simply use those solutions to determine the solution to a bigger problem. So if you were to know, for example, the cost of length 4, of a rod of length 4, and you know the cost of a rod of length 1, well, it turns out that the optimal length for a rod of length 5, that's really just going to end up being the sum of the length 4 solution and the length 1 solution. So you would get 8. So of length 4 is 8, which it's not, I didn't really show that here, but for length 5 it happens to be 10, and For length 4, you would get 2 plus 2 plus 2 plus 2 is 8. And the optimal solution for length 1, well, that's not a very hard problem. Length 1, I mean, there's really only one option, is to cut it, such that it's length 1, so you don't really cut it at all. And that has a price of 2. And it turns out the solution for length 5 rod is just going to be the sum of 8 and 2, which will give us 10. Okay? So let's try to do that a little bit more systematically. We're going to go through the dynamic programming bottom-up approach. Of course, if we want, we can also do one of the two other methods that I went over in the last lecture. We could also do this in terms of recursion, and we can also do memoization, but I'm just going to show you the bottom-up solution for now, just because I find it a little bit easier to see, since really we're just building a table. And the recurrence relation that I'm going to make use of is this one right here that I have in Python code. So what this equation is saying is that the maximum value for your rod of a certain length is just going to be the maximum value of what we have so far, and prices. So our prices array at a certain length plus some cached price, which is basically going to hold the optimal cost of the remainder of our rod. So the first term here is going to consider, a rod of length, J here, and this here is going to be the optimal price for the remainder of the rod. Okay, so I'm going to show you what I mean by that as we actually go through the algorithm. So we're going to start off with our cache. We're going to initialize it such that a rod of length 0 will have an optimal revenue of 0, which is completely understandable. That's our easiest case. Is if we have nothing, well, that's going to have a price of nothing. So it's going to have obviously an optimal price of 0. And then we're just going to initialize the rest of our cache to values that are definitely never going to occur. So since all the prices are assumed to be positive, we're just going to assume that they're -1 at the beginning. And then we're going to do a running max. So we're going to, in this outer for loop, we're going to consider, we're going to try to find the solution for a rod of length I, and we're eventually going to build that up to the final length that we want, and in this case it's just 4. So we're going to compute the solution for length 1, and our max value, which is what we want to find, which is what we're going to put into this cache over here. We're going to initialize it to -infinity so that we can find better maximum values. First step, the first one, we're going to consider prices at J. So we're going to consider a rod of length 1, and we're going to see what happens if we just, well, there's really only one option, is to just cut it at length 1. So that's what we're considering here. So prices at J, that's going to be prices at 1, because that's where we start at. And the price is at 1, so we'll have a rod of length 1. And I'm also denoting it by this, sorry, I'm not denoting it, the cut here yet, but wherever I put this red bar, that's going to correspond to my I value. So what optimal rod length am I trying to compute? So I'm cutting it also at the red line, and that's just going to be prices of a rod of length 1. So price of J is 1, which is 2. So that's this guy right over here, plus what is the optimal price for a rod of the remaining length. So that's going to be cache at 1, because I'm considering a rod of length 1, minus the section of the rod that I just computed the price of. So it's going to be 1 minus 1 is 0. So This is basically the rod of length 1 plus 0, and since a rod of length 0 is already my base case, which is right over here, I already have all this information, and that's just going to be 2 plus 0 is equal to 2. So, and that's really all, that's all that J had to go up to because it's only a rod of length 1. So I only have one cut that I can possibly make, and that's at the end of the rod. So I'm done looping through all the possible lengths within that rod of length 1, and I update my cache to have the maximum possible value, which happens to be 2. Okay, so that wasn't very exciting. Let's try to move on to solving the problem for a rod of length 2 now. Okay, so to solve that, we're going to initialize our max value to -infinity again, and now we're going to try to compute our next candidate for our max value. So first, now you can see what I meant by this line. This line is going to denote where are we going to consider cutting the rod. So I'm going to first consider to cut at the first position such that we have a rod of length 1, and then the remaining section of the rod will also be of length 1. So that's going to be 2 minus 1. So we're going to consider prices of j, which is just prices of 1. So that's going to be this section right over here. So that's this prices term. That's going to have a length of, or sorry, a price of 2. And then we're also going to consider the remainder of the rod, which is going to have a price or an optimal revenue of cash of I minus j, which is going to be just 2 minus 1, because we start off at 1. And cash of 1, well, we already computed that because we cached it, and that's going to have a price of 2. Okay, so this is going to be 2, so my price 2 plus my cash, which is also 2. So 2 plus 2 is 4, and that's my new max value for a rod of length 2. Okay, and then there's another option. Well, we don't have to cut here. We can also just cut at the very end of the rod of length 2. And what'll that be? Well, that's going to have a price of prices at j, so prices of 2, which happens to be 4, plus the cached value for the remainder of the rod. And well, the remainder of the rod is just nothing, because if we cut it here, the remainder of the rod, there's no more of it, because we're only considering up to this rod of length 2. So that's going to have a value of 0. So 2 minus 2 is 0. So, we have our optimal revenue of 0. This is going to be 4 plus 0, which is also the same as the max that we had before. So that's not really going to change anything. So the maximum possible length of a rod of length 2, that's still going to remain at 4. Okay? And you can see what the next step is going to be. We're now going to consider a rod of length 3. Okay, so we're going to move that red line to over here, and now we're just going to consider first the rod of length 1 plus the optimal price of the remainder of the rod. So that's just going to be, so this guy is going to have a price of 2, and then this guy, so of the optimal revenue of length 2, we computed that to be 4. So it's going to be 2 plus 4 is 6. Okay, we're going to consider also cutting it in the next position, such that we have to get the price of a rod of length 2 plus an optimal length of 1, or the optimal price of a rod of length 1. What's that going to be? Well, that's going to be price of 2 is 4, so that's this 4 over here, plus a rod of length 1. The optimal length is just 2 that we computed before, and that is also 6, so that's not going to change anything. Lastly, we're going to consider a rod of length 3, and we'll have no remainder of the rod. So if we look at the prices, well, we have a price of 8 for rod of length 3, and the remainder of the rod is of size 0, so that's going to have no revenue. So that's going to be 8 plus 0, which is 8, which does happen to be bigger than the max that we had before, so we just update our maximum value to be 8. So we update that into our cache, and now you can see we have all of this information for a rod of length 0, 1, 2, and 3. The final step is to move this to the end. Now we're going to finally solve the problem that we wanted to do, which is get the price or the optimal revenue of a rod of length 4. We're going to run our max again, so consider cutting at the first position. So we have prices at 1, which is 2, plus the optimal price for a rod of length 3, which we just computed to be 8. So we're going to get 2 plus 8 is 10. So that's already pretty good. We consider the rest, well, they just don't happen to be quite as good as what we had before. So that's going to be, prices of 2 is just going to be 4, plus the optimal length of a rod of length 2 is also 4, right over here. That's 8, not as big as 10, so we move on. We're going to go here, we're going to get a rod of length 3 is 8, plus a rod of length, the optimal length 2 is 10. That's no better than what we had before, so we're going to remain at 10. And then we consider our just not cutting the rod at all, which is like 4, and that's just going to be 9, right? So it's going to be 9 plus 0 length optimal cost, which is 0. 10 versus 9, 10 is still going to win, and then we update our cache accordingly. And what are we going to return at the end? Well, 10 is just going to be the last value. So the last element of our cache is 10. Okay? So you can see that we did have to go through this entire process. It wasn't going to be trivial. Some of you might have thought that, okay, well, if the prices just keep on increasing, well, I mean, isn't it just going to be, the last element? And you saw here that that's not the case, right? Because, we found a better solution where we cut it up, and, we made use of a smaller optimal problem, which was a rod of length 3, which happened to have a size of a price of 8, and we added that up to another price, which was just 2, and making use of our smaller problem's optimal solution, we were able to get the overall optimal solution. Okay? So all of that was great. We went through the bottom-up approach, we built our table, and eventually we found out what is our maximum revenue that we could get. But practically, this isn't all that we can do here, because that's great that we now know what we could get, but that doesn't really tell us how to get to the solution. Okay? So what I'm going to do, I'm going to show how can we actually reconstruct the bottom-up solution, because that's usually what we care about the most. Okay? So let's talk about reconstructing, and the way we can do that is to just introduce another row of our table, and I'm just going to call it trace. Okay, so we're going to have the same optimal revenue table here, but we're also going to have this trace, and I'm going to let that represent the optimal size of the piece to the left of a rod of length I. So if we were to have a rod of length 4, then so this element here, trace of 4, is going to tell us what should be the length of the piece to the left of it, and that'll tell us where to cut the rod. And then from that, we can just go through our trace array, and then we can just find what is the trace at that smaller rod, and we can keep on working our way down until we reach a rod of length 0, and then all the elements that we find on trace of I will tell us the positions of the rod to actually cut it at. Okay, so this is the code. It's really just a slightly modified version of the previous code over here. Really, I'm just going to build this trace array if we have to actually replace one of the maximum values that we're building up. So let's work through it again. I'm going to go through the exact same process, but I'm also going to show where we change our trace array. Okay, so we're going to start off with computing the solution for length 1, so that's I equals 1, and then j equals 1, we'll be considering basically the left piece. So this is what I mean by the left piece. This guy here is also going to be length 1. Okay, so we're going to, of course, since we initialize our max value to negative infinity, we're going to have to update our max value so that, it becomes, well, it's just going to be 2 plus 0, so 2. And because we updated the max value, we can therefore also update our trace. So our trace at I, so this guy here is going to change to 1. So that means that if we were to consider the optimal solution for a rod of length 1, we need to make sure that we have our left piece has a length of 1. Okay, so that's really just going to correspond to not cutting the rod at all, because we're saying that one part of the rod needs to be length 1, and if if the whole thing has length 1, well, we're not going to cut it at all. So let's move on. And of course, we update the cache to the max value, which is going to be 2. Let's move on to the next optimal size of length 2. Well, we're going to find that when we have j equals 1, so we're considering the cut to be here, well, it's going to be a better solution than negative infinity, which is what we initialize it at. So we're going to have a max value of 2 plus 2, so that's going to be 4, and we'll update the trace such that we cut it at 1. So this 1 corresponds to this position 1 is where we're going to cut our rod, and then we consider another option. Let's suppose we don't cut the rod and we want to have trace at I equal to 2. That's what that would correspond to, having a left piece of size 2. Well, does that get a better value? No, because we're just going to get 4 plus our cache length of 0, which is 4, which is not better. So therefore, we're just going to not update the trace at all because there's no need. Okay, so this is going to be the value of our table. Next, we're going to look at a rod of length 3, so optimizing for that. Consider cutting at the beginning, or to make the left piece have a length of 1. And we'll find that that does do better than just negative infinity. So we'll update the trace accordingly to 1. We then move our cut 1 to the right. And then does this have a better solution than 8? Than 6, right? Because that's just 2 plus 4 is 6. Well, not really, because we're going to just get of length 4 plus length 2, which is also 6. So we don't need to update the trace. But if we now cut right over here, so if we cut at the position such that we don't need to cut the overall rod of length 3, well, that is going to change things because now we're going to get an optimal revenue of 8 instead of 6. So therefore, we update the trace at I to be 3. So that's basically telling us if we're ever considering the problem of a rod of length 3, just cut such that the left part of the rod is length 3, and that's really going to be the only cut that we make. Okay, so we update the cache accordingly, and then now we do our final problem of length 4. So we update accordingly. We're going to get our max value of 10, right? Because we have 2. So this guy is 2 plus the optimal length of the 3 length rod is 8. We get 10. We update the trace accordingly such that we're basically saying that we must have, if we cut it at, or if we want to find the solution for 4, we need to have a rod of length 1 here. We keep going. We're never going to find that we can get a better value. If you remember from our example, we're going to consider this. That's not going to work. We're going to consider this. That's also not going to be any better. We consider this. That's also not going to be better. 9 is less than 10, and so on. So that's finishing that version of the rod cutting problem. And now, the next thing that we're going to do is we're going to make use of our trace variable that I returned here. So I'm going to let this function return this trace, which is just this list over here, okay? And this function is just going to trace through this trace list. So here I'm just calling the reconstruct function that I had before, and I'm just going to extract the trace variable. I don't really care about the cache because I don't need that to trace it. I'm just going to care about trace. And I'm going to set this reconstruction variable to hold all of the positions of the rod that I need to cut at. Okay, so first of all, I'm going to look at the last element of trace because I am trying to solve a problem of length 4. So I'm going to look at the last element, which is 1. So that's telling me that I need to put my red line right at the 1th position. So right over here. And now, after that, I'm going to decrease my length by the value of the trace. Okay, so I'm going to decrease 4 by 1. So 4 minus this 1 over here is going to be 3. And now I'm going to, quote unquote, find the solution to a rod of length 3, which is just going to be this guy over here. Okay, so to do that, I am going to decrease the length. I am then going to look at the trace at my new value of current length, which is going to be 3. Okay, so I'm going to look at the trace at here. And now imagine I'm trying to solve the problem again, where I want to know where should I cut a rod of length 3 now, which is going to correspond to just this part of the rod. So not including this part, but only this part of the rod. And what do I get here? Well, this is saying I need to cut such that I have a left piece that has a length of 3. So that means that I'm going to cut it at 1, 2, 3 on the rod, and that is where I cut it. Okay, so I'll append that. So I'll append the 3, and then I decrease my current length from 3 minus 3 is equal to 0. And that's just going to denote a stopping condition because, as you can see here, I already cut up to the end of my rod. So when I reached a current length of 0, that means I have nothing else to do, and I'm pretty much done. And this is my final solution. So this reconstruction variable is going to hold, it's going to say that I need to cut at 1, so right over here, and also at 3. So 0, 1, so 1, 2, 3, right over here. So this corresponds to length 0 and length 3. Okay, and this is basically the reconstruction or the actual solution that we're going to apply if we actually ever wanted to solve the rod cutting problem for real. Okay. Okay, so that was kind of like a primer to dynamic programming. This was the first real optimization problem that we solved with dynamic programming. And now let's try to move on to another interesting problem that has to do with optimization. Okay. So this problem is called the edit distance, also termed as the Levenshtein distance. And the problem is, let's suppose you are given 2 strings. So by string, I just mean like a word, like maybe like Bob or like boss or something like that. And we want to return what is the minimum number of edits that need to be made to turn one string into the other. And by edits, I'm just going to constrain edits to mean one of 3 different operations. So there is insertion, where we just insert a single character into the given string. Another option is deletion, where we just delete a character. And the final one is going to be substitution, where we can substitute one character for another. So just as an example, let's look at the words bark and bat. So the edit distance between these 2 words would be 2. And that would correspond to deleting the R here and replacing this character K with a T. Okay, so, and of course, the edit distance going from one to another is just going to be symmetric, or kind of symmetric, um, because, to go from bat to bark, the edit distance would also be 2 because we can just substitute the t for a k and then insert an r right over here after the a. Okay, so, and that's the minimum distance between the word bark and the word bat. Okay, so let's try to solve this problem in the general sense. So I'm going to consider two strings, one string of length A and another string of length B. And let's just, in terms of terminology, let's just index them kind of like Python lists. So the entire string x is gonna consist of from 0 to a minus 1. So those are indices. That's what it's going to look like, x of 0 colon a. And y will similarly be from 0 to character b minus 1. So we're going to just denote that as 0 colon b. So that's a string of length b. And that's, oh, whoops. We're going to define the optimal edit distance between these strings to be, let's say, d of between x and y. Okay? So let's try to break it down, what the edit distance really means, because at first when you look at the edit distance, it might be a little bit daunting because there's so many different there's so many different characters that you can insert or substitute, and there's so many different positions that you can insert or delete from. You can already imagine that if you were to try to enumerate every single possible way to do a sequence of insertions, deletions, and substitutions, that's gonna have a terrible runtime if you were to enumerate all of them. Probably has some nasty n factorial factor in there. But as you're gonna see with dynamic programming, we're gonna be able to solve it in, well, not quite linear time, but much better than factorial time. Okay. So breaking down the edit distance, so we're going to consider a couple of different cases. First case over here is, let's suppose we're given these two strings, x and y, and it just so happens that the last character of x is equal to the last character of y. Well, what would be the distance between x and y? Well, that's just going to be the distance of x from 0 colon a minus 1. So the first a minus 1 characters, the distance from the first a minus 1 characters to the first b minus 1 characters of y. And it's just going to be the exact same as the distance from the first, all the a characters of x to all b characters of y. And why is that? Well, if the last characters are equal, we just need to, we just need to find the distance from, the last, or the last a minus 1, the last b minus 1, and then not even worry about the last character because they are already equal. So this is a case where the edit distance is just going to be the edit distance of two smaller strings, where each of them is smaller by 1. So for example, Baba to Borja, that's going to have the same distance as just, well, Bob to Borgi over here, because the A's, these last characters are the same. Okay, so that's the simplest case. A bit of a more complicated one is, what if the last characters are not equal? So if they're not equal, then, well, by our operations that we have, we only have substitute, insert, and delete. Well, we can just break it up into each of those three different cases. So one case is, let's suppose we had, to find this distance, we can consider the distance from the first a minus 1 characters to the first b minus 1 characters of y. And let's suppose we know that distance. Well, we can do that. We can do those edits, and then simply substitute the last character of x for the last character of y. Okay, so how many operations would that be? Well, that would just be the distance of x0 to a minus 1 to y of 0 to b minus 1. So that distance, whatever that optimal distance is, we're not really sure yet, plus 1. So it's going to be 1. That 1 corresponds to the single substitution that we do over here. But that's not the only thing we can do. We can also consider the case where, let's suppose we have x of 0 to a, so all the characters of x, and we're only going to transform that into the first b minus 1 characters of y. Okay, so x of 0 to a to y of 0 to b minus 1, and then we insert the last character of y. Okay, so that'll be one operation plus whatever the distance is from x of 0 to a to y of 0 to b minus 1. And then the last one is deletion. So now, instead of all the characters of x, let's only transform the first a minus 1 characters of x, convert that to all the characters of b, and then delete the last character of x, so x of a minus 1. Then when we do that, well, that's just going to be 1, so one operation, plus whatever distance is from x of 0 to a minus 1 to y of 0 to b. So all of those are valid, and to encapsulate that, I'm going to use this min operation here. I'm going to find what's the minimum distance, or the minimum of all of these three distances, and then add 1, because no matter what, we had to do one substitution, or one insertion, or one deletion. Okay, so that's the second case, and now you can kind of see that we have a bit of a recurrence relation going on. We have our big problem is equal to some function of a smaller problem, right? 0 to a minus 1 is a smaller problem than, so going from 0 to a minus 1 to 0 to b minus 1, that distance, that's gonna represent a smaller problem, which would be 0 to a to y of 0 to b. And you can see all of these are basically smaller versions, smaller problems versus just this big problem here of from all of x to all of y. So the easiest way, and of course, since this is dynamic programming, you can either do this with recursion, you could do this with memoization. I'm just going to go with my favorite approach, which is the bottom-up approach. And to do that, we're going to need a table. So what better way to show these kind of theoretical recurrence relations than just make a concrete example from one word to another word. So let's consider converting the string listen to the string silent. And the way we're going to do this is we're going to basically build our way up, build up a big table until we get to our final solution. So each element of this table is going to represent what is the edit distance, so the minimum possible number of edits to get from whatever this substring is to this substring. So for example, this guy is going to hold what is the edit distance between nothing to nothing. This is going to hold the edit distance between nothing and, well, nothing plus s, which is s. This guy over here, for example, is gonna get the edit distance from, where was that? So that's list, so list, to silen, so silent. And you can kind of see, from these relations, we're gonna keep track of all of these, these distances and work our way down the table here. And so eventually, we're going to reach this last element of the table. We're going to get the distance from listen to silent, which is what we want to do. Okay, so let's initialize our table to our base cases, as we always do. Well, first base case is, well, converting from nothing to any number of these substrings, so nothing to s, nothing to si, nothing to sil. Well, that's just going to correspond to a bunch of insert operations. So converting nothing to nothing, well, that requires, well, nothing. Converting nothing to s, Well, that's going to only require one insert operation where we insert the S character. Going from nothing to SI is just inserting S and inserting I, so that's two inserts and so on. So it's just going to increment all of these accordingly. The next base case has to do with deletions. So going from nothing to nothing is 0, as we did before. Going from L to nothing is going to be one deletion, where we delete the L. Going from Li to nothing is going to have two deletes, and so on. So going from listen to nothing is just deleting 1, 2, 3, 4, 5, 6 characters, and that's just going to be our 6 over here. All right, so now that we have a pretty decent start to our table, we're ready to start making use of our recurrence relations that we drew, or that I wrote a few slides ago. So this is exactly what I mean. So we're gonna try to populate this value here, and I have three possible terms that corresponded to insert, substitute, or delete, and I kind of color coded it here for you guys. So first, this is the problem of going from L to S. Well, we can just compute that. Well, first of all, we're going to see that, well, the last character of L and the last character of S are not equal to each other. So it's not just going to be the edit distance of the first the first A minus 1 characters and the first B minus 1 character. So it's not going to just be 0 over here. It's going to actually be 1 plus the minimum of, what, um, what if we were to do a substitution or a deletion or an insertion. So for substitution, well, this corresponds to going from nothing to nothing, okay, nothing to nothing. So remember the first A minus 1 character, so the first B minus 1 characters of Y. And then we're going to substitute the term L for S. Okay, so that's going to be 0 operations, which we're going to add to the 1. The next one to consider is what if we wanted to do a deletion. So we're going to go from nothing. So remember the first A minus 1 characters of this string L. So that's just going to be, well, nothing, right to the left of it. We're going to go from nothing to all of the characters of our next one, which is S. And then we're going to delete the last character of the first string that we're going from. So that's going to be L. Okay, so that's going to be one operation because we already found in this portion of the table that going from nothing to S takes one operation. Okay? And then the last possible case is the insertion one, where we go from all of the characters of the first string to the first B minus 1 characters of the second string, and then we just insert the last character of the second string, which is S. So in that case, we'll be going from L to nothing, so the first B minus 1 characters, which is just going to be nothing, and then we insert the Bth character, which is just going to be S. And as you can see, well, going from L to nothing, that's just one operation. So hence, now that we've looked at all three of our options with substitute, delete, and insert, well, what's going to be the best one? Well, it's going to be 1 plus min of 0, 1, and 1 over here. So that's just going to be 1. And then we just continue that. So we're just going to continue in our table. And now let's look at the problem going from L to Si. And what's that going to consist of? Well, we're going to consider substituting L for I. Okay, so substituting for L for I, that means that we need to go from the first A minus 1 character, which is nothing, to the first B minus 1 characters, which is now S. Okay, so we're going from nothing to S, and then substitute our last character L for I. Okay, so that's going to consist of one operation. The deletion is going to go from nothing to Si, so nothing to all the characters of Si, and then just deleting the L, the last L character. And so as you can see here, that's going to correspond to 2 operations, which we computed before. And then to do an insert, we need to go from all of these characters to the first b minus 1 characters of si, which is just s. And then we go from L to S, and then insert the I, which actually takes 1 operation that we found over here. So technically, we have 2 different optimal solutions for getting this edit distance from L to Si. We could have either chosen to substitute, or we could have chosen to insert the I. Okay. And then we can continue on this path. So now we try to go from L to SIL. And in this case, well, we don't need to consider all of those min operations like the last example. Since L, the last character L, is equal to the last character of the first string L, well, we don't even need to consider the min. The Levenshtein distance is just going to be the same as the distance of the first a minus 1 characters. So the first a minus 1 characters, which is just going to be nothing, to the first b minus 1 characters of sil, which is si, and which happens to be 2. So this value is just going to copy the values of the top left of this table. So it's going to be 2. And then we continue on this the same process. You guys are probably getting the gist of it. I'll do a couple more examples, because this is probably getting very tedious for you guys. Let's suppose we want to go from Li to just S. We have the option of substituting, well, first going from the first a minus 1 character, so L, to the first a minus 1, or the first b minus 1 characters of S. So that's going to go from L to nothing. And then we substitute the last character I for the last character S. So that's going to be 1 operation. We can also, going from this route, we can go from L to S, and then, so L to S, and then delete the last character, the 8th character of Li, so that'll be I, and then delete that to get the S. And then similarly with insert, we just go from all of these characters Li to the first b minus 1 character, so nothing, and then we just insert the S. Okay. And then yeah, so we're just doing the same thing. We're going to get the minimum of all of these 3, which is going to be one of these 2, so 1, and just add the 1. The next case, going from Li to Si, well, since I equals I, the last 2 characters are equal to each other. That's just going to be the same as going from L to S, and that's it. So that's just going to be 1. Continue building up the table, yada, yada, yada. Not going to go over this in much detail, but eventually we're going to reach the end of our table. So now going from listen to silent, we did all this work to build the table. We finally reached our last step of our problem, and we're going to consider the few different cases of going from, if we're going the substitution route, that means we're going to do list with an E to silent, and then substitute N for T. We could also go the deletion route, where we go from list, so the first a minus 1 characters, L-I-S-T-E, to all the characters, silent, and then delete this last N over here. Okay. And then the insert operation is going from the first all characters, so for all A characters listen, to only the first B minus 1 character silent, and then insert yeah, sorry, I think that should be a T, not an E. Sorry about that. I'll update that for the slides for you guys. But in either case, you should get that the optimal route to take will be the insert operation, so it's 3, and you're going to get 1 plus 3, which is 4. So the final edit distance from listen to silent will be 4. And so this is the code. It's really not that complicated. We're really just iterating through a table. So that's why I have a double for loop. I'm first gonna go over length a plus 1, and it's plus 1 because you'll notice from the table that I left an extra element for the base case of going from nothing to nothing here. Okay, so that's why I have an extra character. So it's going to have the length of the first string. The next loop is going to go over the length of the second string because the table is going to be the product of both lengths of each of those strings. And the first case here, I'm going to convert. I'm going to first start off by converting the empty string to a second string, and then so that's the top row. And then the first column is going to be deleting the first string. So these are my two base cases that I set up here. And then here is the actual recurrence relation, this part of the code. The first one is the easiest case where the last characters happen to be equal. So a of I minus 1 equals b of j minus 1. And if that's the case, then well, I'm just going to take the top left element. So cache of ij is just going to be cache of I minus 1, j minus 1. So it's like, over here, I'm going to set this to just this guy over here. The next one are the three cases, so I'm going to have min. So this case corresponds to substitution. This case with using cache of I, j minus 1 is going to correspond to insertion, right? Because that's going to correspond to the one element to the left, getting that distance. And then the deletion is going to correspond to taking the element 1 to the top, 1 above it. And then no matter what, I'm going to add 1 because I did have to do either a substitution, an insertion, or a deletion. And then I just keep on iterating until I build my table. And the final answer is just going to be the cache, and specifically the last element of the cache. So cache of -1, -1. So that was great, but similarly with the first problem, with the rod cutting problem, I also want to know how to actually trace the edit distance. Sometimes it's nice to know what characters did I have to insert, what characters did I have to delete, and what did I specifically have to substitute, to get from one string to another string. So to do that, we can actually directly use the table that we just made, because if we were able to go, we were able to traverse, we were able to build up the table, well, we should have enough information to know how do we have to traverse back to go from, the final word, silent, to, the first word, listen. So to do that, we are going to trace through. And to do that, all you got to do, start at the last element of your cache, so the bottom right, and we're just going to try to put back together the pieces. We know that 4 is equal to 1 plus the minimum of either this guy, or this guy over here, and we just need to know what it is. So we know that, well, 4 is just going to be 1 plus 3. It's not 1 plus 4, it's not 1 plus 5, we know it's 1 plus 3. So we know that we must have come from here. So that means that one of the operations that we did must have corresponded to inserting a T character. Okay, so remember, every horizontal operation that we do, going from the left element to the, if we were to draw from the left, that corresponds to an insertion. If we draw from the top, that corresponds to a deletion. And if we correspond to a diagonal, that corresponds to a substitution. And yeah, it's only a substitution if these characters are not equal. If these characters are the same, then we know that we are going to just do really nothing, really. And we will need to go up a diagonal, which I'm showing right here. So imagine we're here, we're at the we've now gone back a step where, we went from listen to silent, and now we observe that n is equal to n here, right? So these two are the same. That means that we really didn't have to do any operations here because, from silent, or from silent to listen is just going to be the same as sile, so S-I-L-E to L-I-S-T-E. Okay, oops. And then, well, hold on, S-I-L-E to L-I-S-T-E, well, the last two characters are also the same. So we're just going to go up one, up the diagonal, and we're not going to infer any operations because we didn't need to do any. Next, these two characters, T and L, are not the same. So we need to consider each of the three elements to the left, to the diagonal, and to the top. We're going to compare 3, which is this guy, and that's going to be equal to 1 plus one of these two elements. Not only one necessarily, but at least one of them. And, we might see first that, oh, it's equal to 1 plus 2, which will correspond to deleting this value of t. Okay? Now note that, well, there's actually another solution we could have done, which is going up the diagonal because, 3 is also 1 plus this 2 over here, and that would just correspond to substituting s for the character L over here. Okay, so there's never going to be one solution to your edit, the trace of your edit distance. But there will always be a unique edit distance itself. So it's always going to be 4. We just need to, there might be different ways of getting to that 4. And then next, we go here, S is not equal to L, so we again need to consider the 3 cases. And we can see here that 2 is equal to 1 plus only one of these, so 1. So that means that we must have substituted S, this S over here, for this L over here. Okay? We don't need to do operations anymore because, we go up here, I is equal to I, so nothing needs to happen. And then we go up again. Well, again, a few different, well, actually, no, sorry, only one answer here. 1 is equal to 1 plus 0, not 1 plus 1 or 1 plus 1 here. It's 1 plus 0, so that means we must have substituted an L for an S character. And now we reached the top left. There's really no more operations that we can do because we've reached nothing to nothing here. Okay, so and now that we've traced through our table, all we have to do is read all of the different operations that we did in reverse order. Okay, so in reverse order, we substituted L for S. Okay, so that was this last operation here. We substituted L for S, so that means listen would turn into sissin. So we substitute this L for an S character. So that was this. The next operation was substituting S for L, so that's this arrow here, which would correspond to this S corresponds to, so this S substitute for an L, so it becomes Silton. And then we go to the next character, we're going to delete the T, okay, so cross it off, so Sistin becomes, this T here, so we are going to delete it, Silton becomes Sillin, and then we just need to do a final insert of T, which is going to be right over here at the end, so Sillin becomes silent. And you can see we did only 4 operations, so that corresponds to the edit distance. Okay? So the code for actually getting the solution, really it's just going to make use of the cache that we just built. So what we're going to do is we're going to start off at the bottom right of the cache. That's why I'm going to initialize I and j to be len of A, len of B, and I'm just going to keep on iterating, I'm going to keep on decreasing I and j to work my way up and to the left of the table until we reach the top left of the table. So this if statement corresponds to, well, let's suppose the characters, at those positions are actually equal to each other. That means the last characters are the same and we don't need to do any operations. So I'm just going to decrement both I and j, which is corresponding to just going up left 1. The next case is, what if the last character, um, so cache of ij is equal to cache of ij minus 1 plus 1. Okay, so that means that the cache right to the left of it plus 1 is equal to cache of ij. That means that we must have done an insertion. Okay, so yeah, excuse this typo here, that there should not be a no. It's just, it signifies an insertion, not a no. That was probably a copy paste error. Okay, so that corresponds to an insertion. And then after we do that, we just decrement the column by 1. So we do j minus equals to 1. And then we have cache of ij equals cache of I minus 1, j plus 1. That corresponds to whether we deleted a character. And then, we decrement our row. And notice that I'm also appending to my solution a few of these strings here to denote that we inserted a character or deleted a character. And the last case, which is really the only possible scenario, is that we have to substitute. So we substitute a of I minus 1 for b of j minus 1. And then since we're going up diagonally, that's going to correspond to I minus equals to 1 and j minus equal to 1. And then we return the solution, and eventually you should get these values, or these insertion, deletions, and substitution sequences over here. Okay? So that is the edit distance, and a few applications of the edit distance. If you're ever wondering how does your editor, so like let's say Microsoft Word or Google Docs, they typically have a spell checker in them. Well, the way that they actually work, they typically use this edit distance metric, because whenever it suggests another word that you probably meant to use, well, how does it find that word? Well, the text editor has a dictionary of a bunch of different valid words, and what it does is it'll try to find the smallest edit distance between the word that you did not spell correctly and a word in its dictionary. So whichever, maybe the top 3 contenders, so the smallest 3 edit distances between your dictionaries, between your word and the dictionary words, those would be the words that it actually suggests to you. Okay. Another application is finding the longest common subsequence between 2 strings. So that that's important if you want to know how similar 2 strings are from each other, and that really just corresponds to the edit distance where we remove the substitution operation, and that can also help with approximate string matching. So matching 2 strings together. Sometimes there is an application in regular expressions, so that's almost a topic of its own, to find out whether parts of a string are actually located in another bigger string. So that has a lot of applications in general with in software engineering. And then another application is in DNA sequencing. So in biology, you probably are aware of DNA that basically consists of a bunch of different nucleobases. So like you have G, guanine, C, cytosine, thymine for T, adenine for A, and those basically make the building blocks of life, really. A very common application is sequencing, is to determine let's say how different one set of DNA, which of course which just consists of G, C's, A's, and T's, how similar is one set of DNA from another set of DNA? So that's called sequencing. You might be aware if you took biology that certain sequences of DNA can correspond to different proteins that that can be made, which consist of amino acids. And the edit distance is a very, very common metric, um, to know how similar perhaps two organisms might be from each other by using the nucleobases of DNA. And as you're going to find in our last and final lab, so lab 5, we're going to try to make use of the edit distance for one of the bonus functions of that lab. Okay? All right. Um, so that pretty much concludes what I wanted to talk about with dynamic programming. Remember, all of this material, dynamic programming and game tree search, all of that is bonus material. So lab 5, even though there will be a dynamic programming related question, that's only going to be for bonus marks, and any question that may or may not be on the final assessment, um, if it has dynamic programming or game tree search, will also be bonus. Okay, thank you very much, and have a great rest of the semester. Bye.